All right, hey there. So, welcome back to Intro to COG. We just went through a series of lectures involving the use of and the design of various neural modeling approaches, right? So, modeling a single neuron to try and get that working, and then scaling up to what can a group of neurons accomplish, all the way up to some crazy things we saw, you know, these algorithms competing against each other to make very wild and interesting predictions and creating images that very fool us very easily, that kind of stuff. Um, so the idea is neural networks really help us with our big framework, the big idea that minds are these information processors, right? We're trying to understand minds. We're trying to understand cognition, especially on the human level, but sort of in any way. And by diving deep into the mechanics of one of those networks, we got to see how you could really explain how complex processes and then leading to different complex behaviors like we're able to do every day um, can emerge from that, like just the interconnected structure of the network, right? So from the bottom up, we start to create these huge arrays of mathematical functions and other cool things out of that, right? So, but today we're going to talk about how to extend, and for the next couple of lectures, we're going to talk about how to extend this forward a bit. There are ways to. The question ends up being, how can we make, the first dabbling with neural networks is, ooh, can we capture the and operator, right? Scaling up into maybe picture classification, that sort of thing. But the question that stands is, how human-like is this? Just because we're able to sort of pin down the way that a single neuron works, and not sort of, we pin it down pretty well, and the models only get more robust with time, but does this work? Is there something else about the brain and the way that we work that is not easily explained by these systems? And so that opens the door into a broader field of trying to understand different actual human phenomena using these neural network approaches. So today we're gonna jump straight into an example that is pretty challenging for this approach, because it seems like it would be so much better suited to something like the uh, physical symbol system hypothesis as opposed to the neural modeling approach. So language, right? We've talked multiple times about language, how useful it is and how powerful it is, obviously. And it's one of the most useful tools we've ever developed in our cognitive toolkit. And it's huge. It's rooted in everything. Language can influence. It is influenced by and can influence all of these things. Your cognition, your emotion, how you interact in social groups, both like the abstract and concrete. So you can relay messages about how exact things that happened to you today, and then also theories about why your boss behaves that way or whatever. That kind of stuff. And language, as we've looked at from a few different angles, it's this very rule-governed activity, right? We're able to learn all the rules of language and apply them every day, even if we don't really know them, right? Like, you ever diagram a sentence in a class, you're like, dang, I didn't know these things were so complex, right? I just spit them out all day. So the question is, how the heck do we get to that point? And what would different approaches say about it? So, you know, understanding language, it's all the symbols, right? They are, you have to understand them. You have to get their meaning and their syntax. You have to, the rules of parsing a sentence help you understand the meaning of the sentence, but you also need the symbols to attach to something in the world, right? We've talked about this several times. If you recall this example, here's a sentence: the lazy cat recently had a, and it ends with a period, which has, all those things have different semantic meanings, but the syntax shatters. There's no meaning, or there is no good way for your brain to finish this miserable sentence. It has violated your syntax knowledge. You still know the semantics of most of it, though, and how the words relate to each other. You can think about the fact that this cat recently had a problem. You might be able to fill in what the cat recently had whereas on this side, this is the famous Chomsky sentence, colorless green dreams sleep furiously. That doesn't mean anything, right? It's perfect syntax. It doesn't trip your syntax sensor in your brain, right? It just doesn't mean anything. The content of those words don't really go together, right? A colorless green thing, well, that's ridiculous out the gate. Dreams aren't necessarily colored, and I mean they may have colors, but they don't have the property of a color, right? And do dreams sleep? And if they sleep, do they do it furiously? Again, this is ridiculous. And that's the whole point of the sentence, and the reason that Chomsky chose it to illustrate these points, right? So we have these two different scenarios, and your brain is very adept at parsing them both. We'll go back and do this again. We did it a little bit before. Remember, this is a toy grammar, so don't come at me on my linguist friends. But it's like a toy grammar of producing rules that would help you parse a sentence's syntax, right? So the lazy cat recently had it starts as a sentence, and then it breaks into noun phrase and verb phrase. And again, we keep expanding these things until we get to a point where we can label every part of the sentence, right? The is a determiner, adjective, lazy cat, etc. And when we needed a noun in our tree to not break, the noun, it falls off. So this sentence ended up violating our syntax rules, whereas colorless green dreams sleep furiously does not. It happily fits into all the different categories we need, right? So there's different ways of thinking about this. Remembering that our main goal is to be able to talk about these things in terms of how might a physical symbol system handle learning, understanding these rules and applying them, and how might a neural modeling approach understand these rules. So one thing to talk about first is what exactly, how exactly do we use these rules, right? And there's two different approaches to understanding this. There's the weak understanding of rules. So maybe we understand the rules of language, but we don't actually store them, right? They're just sort of baked into our neural networks, right? We don't have direct access. I can't go in there and say, yes, this is where the verb phrase expansion rule lives, right? But I still can use them, and I can even sort of reflexively understand them. That's how we could still have linguistics under the weak view here, wherein we understand how our system works, but only by studying it, as opposed to just directly understanding it. Versus a bit different approach, which says we do store a representation of those rules somewhere. We keep them. It's not just tunings. It's a set of clean rules that we can look up, right? And that makes sense on the surface as well, right? That there is very much the possibility that, especially when you're learning a new language, right? You start to learn the conjugation rules, and those are words you never even knew before, but they now serve as this sort of point of reference. Now, those two scenarios both kind of make sense, right? I can still totally understand something, how it's used, without actually understanding it, its exact rules. But we can also, we can use rules to understand our own, to build our own behavior out, right? Like when you're learning to parallel park. I've used parallel parking before a few times. When you're learning to parallel park, you start with those rules. You kind of break them down. You do them step by step until they start to flow together, right? So the question is, do we actually store these things, these rules, in our brains as something that is clean and symbolic, or do we not? And do we not even bother? Do we just absorb language rules as we grow, and then we apply it all day? In the physical symbol system world, we remember that all the symbols have to be defined clearly, right? So Physical symbol systems have the following properties: the basic symbols, the expressions, the processing of all the rules, right? And in that world, there's no chance you can't have the weak interpretation because the rules are either defined somewhere or they are not, right? So how do we make sense of the learning process of picking up this these language rules under the physical symbol system? We've talked a lot about learning in neural networks. We actually saw how that process works, sort of. You train the network on error signals, and you update its numbers, and it behaves differently next time until it finally kind of finds the right path. But a physical symbol system, the learning also must be very explicit. So how do we think about learning in that world? In the language of thought, you can learn by way of a specific process. So the sentence "Felicia is tall." How do we learn what that sentence means? So I can't use English to learn. Obviously, I'm learning English. So we use the internal rules of the language of thought, right? So what are the language of thought rules about learning the meaning of this sentence? So it's all logic, right? Formulate hypothesis, test it, and then update. So first the question is who or what is Felicia? What does somebody being tall imply, right? So trying to understand the meaning, trying to acquire this new sentence is spoken to us and we want to understand it, we have to do this sort of explicit hypothesis testing. So it works. I mean, that would work, right? You could have that process of explicitly trying to learn the rules of every single symbol that comes our way, and then learning how they are applied to one another, and then updating them and changing them. And to an extent, that's not a bad way to describe a lot of what does actually happen in the way we learn. But the question is that the core of it? Is there a deeper way to explain this? And that's where when we're talking about neural modeling approaches, at least for science as opposed to applications, we're trying to understand: is there a more neurological explanation, right? So I wandered a little bit forward, but the idea here is that the question is this a satisfying approach, right? It's a bit rigid. You'd have to have a lot of explicit processes going and changing and altering our symbols and rearranging things and making sense of the world in that way. And it comes with this interesting baggage. Language of thought, you have to have a lot of those rules baked in when you're born. This is actually what Chomsky was saying in that interview we watched, right? Way back, long ago. He was going on about how, well, it seems like there are certain in-baked rules that allow us to acquire other language. But that's fine, that's useful, especially because he's focused on the linguistics and how they work. He's less focused on the biological underpinnings. But now that we're in a world that really is focused on them, that there's an alternative way to describe all of this. So with the weak interpretation, right? Remember what that is. It's the idea that you can learn rules, but you don't necessarily understand them, right? So the idea is that there are times when we actually learn to intuit certain things, like certain rules and usage. Maybe you learn a slang term that you don't actually know the meaning of, but you're still able to apply it, right? So the weak interpretation is still compelling, right? There's this idea that, well, I don't have to fully internalize everything to be able to use it. I can pattern match on the world and get by pretty dang well. So the question is, should we be thinking about these rules as these explicit symbolic rule sets, or should we be thinking about them as just the ways that different networks of our brains have been trained up to a certain sort of pattern of activation? So there's this nice overlap between the physical symbol system and especially the language of thought with language rules, right? But because it's all language, it all seems like it would make sense. Like if language can apply and affect language understanding, then maybe it's all language all the way down. But here's the trick. Here's the thing that a little piece of the puzzle that it's important to keep in mind. We are not Wile E. Coyote. We don't have to understand and or internalize the rules of physics in order to fall. He did. He would walk out over the cliff, look down, then fall in a comedic fashion, which would be utterly violent in real life. But he's a cartoon, so it's fine. He only responds to the rules of the world once he understands them, but that's silly. It's cartoonish. The question from the other end is the idea that we can get words in context, we don't know their definitions, but we can still apply them, we can still understand them to some extent. That's interesting. A physical symbol system couldn't handle that sort of uncertainty, right? That sort of missing chunks of the usage of a term, right? But we can totally do that. And this looks a lot like what we've discussed: graceful degradation, partial matching. You don't have to internalize you don't have to receive all of the information to sort of get the picture, so to speak. So, how do we think about neural accounts of language learning? And in neural world, you don't need to store any rules at all, right? You store them in the sense that you store them in the pattern of the way that the network moves information around, right? So the XOR perceptron, right? It doesn't store the function table. It doesn't store the transformation rules. It doesn't have them stored somewhere in it. And it just does the proper outcomes. Given the right inputs, it just spits out the right outputs. That's solid. That's a nice and simple approach. But it's a bit of a black box, right? It can be hard to discuss what's going on in one of these networks because it ends up all being math. So there are drawbacks to this. But the question at hand is language, can we capture certain parts of language using these neural modeling approaches? So let's talk about a category of language learning that has been investigated in this way. So learning past tense. Y'all, you maybe don't appreciate it often enough, but English is a bizarre language. There's all kinds of stuff that makes no sense to an outside learner. We are all very lucky that we learned it early when our brains were still flexible, right? But the idea is here we're trying to talk about past tenses, and this isn't just English, right? Other languages have strange special cases for tenses, but in English, we have past tense words end in ed, right? Baked, walked, danced, that kind of thing. But we learn all kinds of irregular exceptions, right? Gave, not gived. Went, not goed. Fought, not fighted. And the error that you make, the gived, the goed, the fighted, is called over-regularization. Children exhibit this a lot. They engage in, they're learning, they're trying to figure out the world. You may have met a few that do this. You may have been one. It's a natural part of learning the language. You learn, oh, it's so easy to do past tense, but then somebody says, no, there are several examples that don't work. Or you learn more one at a time, right? You say goed, and someone says, what are you talking about? And then you say, I don't know. And they say, went? And then you say, oh, yeah, I'm sorry. So you learn through error in the real world, right? But the question is, that kind of over-regularization is a pretty consistent thing. And the way to categorize this is you have two different categories of tenses, right? You have the irregular tenses and the irregular tenses. So your approach is to learn the regular patterns and then learn all of the irregular exceptions. And this is the very like PSS way, right? So the basic physical symbol system approach is that you take the explicit representation, and then you learn the exact rule of apply ed to words, right, to make them past tense, and then have a special lookup table that is like a set of exceptions to the rules that you then will, in the same way, apply. So But the question at hand is, do I need to do this with a set of with these explicit sets of different, erroneous, irregular verbs? Do I need to store a list of these things to make sense of them? So this is the pattern described there. That is, you would have you give a verb stem, right? I'm trying to apply a new tense, right? So I give it bake. The regular route is you just apply the rule, make sure ed are the last two letters, done. But if I give go, well then I have to, I will try to do the regular route, but I then consult a list of exceptions and oops, oh, went is the right thing. And until that list is compiled, I will make the goad error, right? But let's look at this from a different angle, from the neural network world. In neural network land, you don't necessarily need any rules to be explicitly encoded or taught or picked up. Rumelhart and McClellan, they're a very famous pair, built this neural network, and it has four distinct areas. The approach being, can we make a system that's able to learn these rules and do it without being explicitly taught a symbolic structure like what we just saw, right? Can we just make it so that it's able to output the correct letter encodings? So there were four distinct networks, not a multi-layer network with multiple layers, but they were sort of created separately, trained on different things, all that. So let's break down how the information moves through the Rumelhart and McClellan's networks. So first, input. The input network is phonemes, so the pronounced bits. When I say cat, that's chopped up into a couple of different ways. I'm not an expert on phonemes, but the sounds that they make are the inputs. And so, to pause before going too quickly forward, as long as you can encode something in to be an input for as long as you can give a unique encoding for something, you give a phoneme and it activates the network in a unique way, then you can give whatever you want to a neural network, and it will start to do its training processes, right? Next, we have two little networks. We'll cover them in a next slide, a little more depth, but the idea is that the phonemes can be broken down a little bit more into sort of the little pieces of the audio data that will be turned into, and then maybe the features, right? And the idea is that the network will be active in a very specific way that sort of represents the way that the phonemes came in, right? As this sort of root, the root representation, and then the weightings between that network and the next network in the middle is what converts it into a past tense word, right? So then you start to output. You take the WCL features back, and then you reproduce phonemes. So this network altogether, this set of networks, takes in a bunch of words. It'll take in one word at a time, and it's able to output the past tense of it. Now the question is it making the errors or not? And let's actually follow through a little bit here. So the input on the left, we talked about how the phonemes will come in. They will sort of activate the phonological network in whatever, it breaks down the speech into phonemes. And then those will then map to the first WCL feature network, which is sort of this is getting at the idea of how, as you get further into a network, a neural network, especially very complex ones, the way the data takes shape becomes more and more like small and strange and sort of interconnected as very distributed information, as opposed to sort of a neat, clean symbol like we've been talking about so much. So this first layer takes the WCL features, and then again the connections between those WCL features to the WCL features for the next layer. The way that the weightings work is it will convert the normal tense Wickle features and then change them into a past tense set of Wickle features, which are then in the reverse process of the first step. You get the phonological representation back, so you could speak it out, right? So, cool. I think we understand a little bit about how this system works. And again, a famous model. Okay, so now the question is, how does this map to the way that actual learning of these things takes place? So, the way that theirs worked was on the regular verbs, on the regular words as inputs, the network was able to learn pretty regular on the regular verbs. It was a normal learning curve, right? You have a lot of learning to start and then some diminishing returns. It narrowed in on that pretty quickly. Now, it has this separate shape for the irregular verbs, which took a lot longer. They followed slowly, and the network would learn to categorize them differently, right? Which shows that over-regularization, right? So it would, for some time, irregular verbs are swept up in that top line, but then they start to, the accuracy rate starts to rise as they come down, right? A little bit messy way of looking at this graph, but the idea is we see a normal learning curve for regular verbs and a pretty abnormal learning curve for the irregular verbs, right? But they still come along. They're just behind in the regular verbs. So you have those phases of irregular or of over-regularization. So, yeah, the regular verbs were picked up faster, and then the irregular ones came following after. So this was cool. There's some success at mirroring how tense learning is typically experienced, right? We see just a neural network, a set of neural networks, able to kind of capture this facet of learning, of human learning, that maybe we hadn't seen before. So, but there's an issue here. This model, was developed further by these kinds of questions. Let's say, hey, what's this talk about Wickle features? Why are we doing this very specific, like training of very specific sub features, right? Why are we concerning ourselves with that when you could just handle this with, again, multi-layer networks, right? And because the issue here is that this is sort of the halfway step between a physical symbol world where you're explicitly defining the rules, right? And the complaint was that Rumelhart and McClellan's model was sort of, it was never really going to fail because the way that Wickle features work, these specific little features that the modelers picked out and started developing with in mind. So the question is, asked by Plunkett and Marchman, and that is, can you just do this with hidden layers? Do you need like kind of a special Wickle feature layer thing, or can we just have a bunch of anonymous middle ground layers that help to learn these same kinds of things, but they do it on their own, as opposed to being trained in this specific strange way of, oh, I have this set of Wickle features I believe exist, and I will, train me. In fact, there's a little spoiler here. This ends up being kind of it's a way of understanding how middle layers actually work, because they just do it automatically. You don't have to specify what's to be learned in the middle layers because they just exist to enhance the computational power. So their approach was, hey, we're not going to give any special understanding to these middle layers of the neural network. You're just going to train it like we would train any other neural network. Same inputs, same outputs. Phonological stuff comes in, phonological stuff goes out, right? So here's the thing. They found that the simulation closely matched a human in terms of the way its growth of its performance with irregular verbs versus regular verbs. So it slowly learned to approach, full language acquisition at kind of the same rate. Not necessarily same exact, because the simulation is learning in terms of vocabulary words fed into it, whereas the child is just aging in months, right? But the idea is this kind of simulation, as you watch the training happen, it follows the same trend, and it scales nicely and it matches pretty well. Not perfectly. There's plenty of other things going on in a human that makes them perform differently, but the pattern is there. So Plunkett and Marchman's just a hidden layer model um, has these more gradual changes in performance, and a little bit less of sort of the aha moment. At the start, it over-regularized, it added ed to every word, and then it learned more and more irregular verbs as it went. So this has been our first lecture discussing the ways that we've used neural networks to sort of understand better how humans are behaving. Now, this one isn't saying necessarily that child learning of language is explicitly only, and like all learning is explicitly only neurological. There's no symbolic, usefulness. Because, well, as we discussed before, certain things can be sort of bootstrapped from symbols. I can read instructions for a recipe on a page and then convert them into something useful for me, right? So it's not an exclusively either or, but we're seeing that the way that children learn language is a little bit more bound to the way that neurons work, right? We could, if this network may exist inside a child who is learning a language, and it grows at this rate that we're seeing here. So, and we've done it with no symbolic representations. The weak understanding of language is possible here. All we've done is wire up lots of inputs and outputs and let training processes take care of the rest, right? Tell them no when they're wrong, tell them yes when they're right. Yeah, so that's it for this one. It's a little bit shorter. So I'm hoping to have a couple of these up shortly, but you'll hear from me. Thank you so much. Take care. I hope you're well.